Right now, for human beings are doing something that no living person has done in over half a century. They are flying toward the moon. And the thing that should terrify you is not the journey out. It is the journey back. Tonight, the world is watching Artemis to break records. The headlines are celebrating. The social media feeds are filling up with awe and wonder. And buried underneath all of that celebration is a technical detail that almost nobody in the mainstream is talking about. A detail that engineers have been quietly losing sleep over. The heat shield on the capsule bringing those 4 astronauts home has only ever been tested at full scale once. And that one time, it did not behave the way anyone expected. Before we get into what actually happened, let me give you the picture of what is unfolding right now in real time. 4 astronauts are currently hurtling through deep space at roughly 2,000 miles per hour. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian astronaut Jeremy Hansen. Together, they form the first crew to travel beyond low Earth orbit since December 1972. That is 53 years. It's more than half a century during which no human being got anywhere near this far from home. The numbers alone are enough to rewrite the history books. Artemis II is expected to reach a maximum distance of approximately 252,000 miles from Earth. During its lunar flyby, that breaks a record you would never expect. It does not break the record of a triumphant Apollo landing mission. It breaks the record held by Apollo 13, the mission where an oxygen tank exploded 200,000 miles from home and engineers on the ground had to invent a rescue plan using duct tape and improvisation. That record was not set because anyone was trying to go far. It was set because the trajectory that saved 3 lives happened to swing the capsule further than any human had ever been. That record has stood for 53 years, not because nobody wanted to break it, but because nobody went back. Tonight, Artemis II breaks it on purpose, by design. With a crew that was chosen, trained, and sent out there intentionally, Christina Koch becomes the first woman in history to travel beyond low Earth orbit. Jeremy Hansen becomes the first Canadian to leave the Earth's moon system entirely. These are not small footnotes in a press release. These are the kinds of milestones that get carved into textbooks, the kind that people tell their grandchildren about, and the world knows it. The media coverage has been glowing, triumphant, a return of the human spirit to deep space, a vindication of the long-dormant dream of exploration, and in one very real sense, all of that is completely true. The records are real. The milestones are real. The crew is out there right now looking back at a planet that looks small enough to hold in your hand. But here is where I have to stop and tell you something the celebration is not saying. The mission does not end when they fly past the moon. It does not end when they break the distance record. It does not end when they witness things no living human has seen in more than 50 years. The mission ends when they come home. And coming home means something that most people have never really thought about. It means slamming back into Earth's atmosphere at 25,000 miles per hour. That is Mach 32, fast enough that the air in front of the capsule has no time to move. It compresses so violently that it transforms into plasma, glowing, electrically charged. Superheated plasma reaching temperatures around 5,000 degrees Fahrenheit, wrapping around the outside of a capsule where 4 people are sitting. The only thing standing between those 4 human beings and that plasma is the heat shield. And the heat shield has only been tested at full scale exactly once in history. And that test revealed something that nobody had predicted. Something that engineers did not see coming, even after decades of ground testing and computer simulation. Over 100 chunks of the heat shield material broke away during re-entry in ways that no model had forecast. The capsule survived. I want to be clear about that. The mission was uncrewed, and the vehicle made it back. But the behavior of the heat shield was outside the predicted envelope. And in aerospace engineering, that is not just a problem. That is a warning of the most serious kind. Because when a system fails in exactly the way your model predicted, you understand your system, you fix the flaw, and you move on with confidence. But when a system fails in a way your model did not predict, you have discovered something far more uncomfortable. You have discovered that your model of reality is incomplete, and that is where we are tonight. 4 astronauts are heading toward the moon in a vehicle whose heat shields showed unexpected behavior during its only full-scale test. NASA has made changes. They have adjusted the re-entry trajectory. They have modified the material. They believe the problem is understood and the fix is sound. But here is the question that sits beneath all of that. The new configuration, the new trajectory, the modified material. None of it has ever been flown before, not once. The first time it will be tested under real lunar return conditions is when those 4 people are sitting inside. This is the story of Artemis II, not the distance record, not the lunar flyby, not the eclipse the crew is about to witness from beyond the moon. The real story is whether the system designed to bring them home actually works when it matters most. And right now, with the Earth shrinking behind them, that answer is still unknown. Stay with me. Because what happens next changes everything you think you know about this mission. There is a moment in every great space mission where the wonder and the danger exist in exactly the same place at exactly the same time. For Artemis II, that moment is happening right now, and it is extraordinary. But the closer you look at what this crew is about to experience, the more you realize that every second of it is only meaningful if they make it home alive. The lunar flyby window is approximately 6 hours long. During that time, the Orion capsule will pass roughly 4,000 miles above the surface of the moon. To put that in perspective, the International Space Station orbits Earth at about 250 miles up. This crew will be flying past the moon at more than 16 times that altitude, and yet they will be close enough to see geological features with their own eyes, close enough to document things that no robotic camera has ever captured from a human perspective. Now here's where it gets genuinely fascinating, because this is not just a sightseeing trip. The crew has been trained to target specific regions of the lunar surface with scientific precision. Chief among them is a place called the Oriental Basin. It is one of the most important and least studied impact structures in the entire solar system. Around 3.9 billion years ago, something massive slammed into the moon with such force that the shockwave rippled outward like a stone dropped into still water. Those ripples froze in place. They became a series of concentric mountain rings that are still visible today, perfectly preserved. Because the moon has no weather, no erosion, no geological activity to disturb them. It is a snapshot of the violence that shaped our solar system, locked in stone for billions of years. Scientists have been studying it with robotic arbiters for decades. But there are things the human eye catches that algorithms still miss. Subtle color variations, shadow geometry, the way ejected material fans out from the point of impact. The crew of Artemis II has been trained specifically to recognize and document those details in real time. They are not passive observers on this flyby. They are active scientific instruments. But the Oriental Basin is not the only target. There are lesser-known features that the crew is tasked with observing. Fresh impact craters with preserved ray systems that tell scientists how recent the collision was. Regions near the edge of the far side that expose subsurface material that no mission has ever properly examined up close. These are not tourist stops. They are data collection opportunities that only a human being in the right place at the right time can fully exploit. Because geology still requires something that no algorithm has perfectly replicated. The ability to look at something unexpected and say that does not match what we thought, something here is wrong. Something here is new. And then comes the moment that sits above all of it. Roughly 1 hour into the flyby, the Orion capsule will pass behind the moon from the perspective of the sun. And the crew will witness something that fewer than 30 human beings have ever seen. A solar eclipse viewed from the far side of the moon. The sun, which from Earth appears roughly the same size as the full moon, will vanish behind the lunar surface. And in its place, if conditions cooperate, they will see the solar corona, the outer atmosphere of our star. Faint, structured, alive with magnetic loops and plasma streamers tracing the invisible architecture of the sun's magnetic field. Scientists have chased solar eclipses across continents for centuries just to see a few minutes of that corona. This crew will see it from the other side of the moon. And this is happening at a particularly charged moment in the solar cycle. The sun is near the peak of its roughly 11-year rhythm of magnetic activity. A specific region of intense sunspot activity has already been generating significant flares in the weeks leading up to this mission. What that means for the corona observation is that the outer atmosphere of the sun may be more dynamic, more complex, more visually and scientifically rich than during quieter periods. An active sun produces a corona that is alive in ways a quiet sun simply is not. The crew may be looking at our star in a state of elevated magnetic energy that only comes around once every decade. But here's the thing I keep coming back to, and I need you to hold this thought as we move through the rest of this story. Every photograph this crew takes during that flyby, every geological note, every second of that eclipse observation, all of it lives inside the Orion capsule. And the Orion capsule has to survive re-entry for any of it to matter. The science only reaches Earth if the heat shield holds. The records only stand if the crew comes home. And then something happens that most people watching this mission do not fully appreciate. Something that adds a completely different kind of weight to everything the crew is experiencing up there. For approximately 40 minutes, the Orion capsule will pass behind the moon and disappear. Not metaphorically, literally. From the perspective of everyone on Earth trying to communicate with them. Those 4 astronauts will vanish. No signal can penetrate 2,000 miles of solid rock and the entire global network of deep space communication dishes. The most sophisticated communications infrastructure humanity has ever constructed goes completely silent. Mission Control in Houston cannot send a command, cannot receive telemetry, cannot hear a single word from the 4 human beings who are at that moment the most isolated people in the history of our species. The spacecraft is designed to handle routine anomalies autonomously during that window. Its onboard computers carry pre-programmed contingency protocols for minor fluctuations in pressure, temperature, and navigation. But anything beyond a defined category of manageable situation, and the crew is entirely on their own. No engineers to consult, no ground support to call. Just for people and the machine around them, behind the moon, further from home than anyone alive has ever been. And that 40-minute blackout, as unsettling as it sounds, is not the blackout that worries me most. The one that worries me is shorter. It lasts only 4 minutes, and it happens during re-entry, because during those 4 minutes the heat shield is either doing its job or it is not, and nobody will know which until it is already over. Let me take you back to November 2022, because everything happening tonight. Every decision that was made about how this mission would fly, every engineering choice that 4 astronauts are now staking their lives on, traces back to a single moment when engineers pulled a capsule out of the Pacific Ocean and found something that nobody had prepared for. Artemis I launched in November 2022. It was uncrewed by design. That was the entire point. Fly the rocket, fly the capsule, send it to the moon and back, recover it from the ocean, inspect every inch of it. Confirm that the system works before you put human beings inside. That is how responsible space programs are supposed to operate. You test the machine before you trust it with lives. And by almost every public measure, Artemis, I was called a success. The rocket performed. The capsule reached the moon. The trajectory was executed. The splashdown happened. The vehicle was recovered. But here's where the story gets uncomfortable. When engineers began their detailed post-flight inspection of the heat shield, they found something that none of their models had predicted. More than 100 distinct regions where chunks of the heat shield material had broken away during re-entry, not worn away smoothly the way the design intended, not eroded gradually in a controlled and expected pattern, broken, fragmented, ejected in irregular chunks across different sections of the shield surface in ways that the computer simulations had simply never forecast. The capsule survived. The internal structure remained protected. There had been a crew. The thermal loads transmitted to the cabin would have stayed within survivable limits. So in the most fundamental sense, the system did not catastrophically fail. But here is the distinction that matters enormously in aerospace engineering. Surviving is not the same as performing as predicted. And when a system performs outside its predicted envelope on its only full-scale test, that is not a minor footnote. That is a signal, a serious one. Think about it this way. If a system fails in a way that matches your model, you understand your system. You know what went wrong? You fix it precisely and you move forward with justified confidence. But when a system fails in a way your model did not anticipate, you have a deeper problem. You have discovered that your model of reality is missing something. And if it is missing one thing, you have to ask yourself honestly what else it might be missing. The material at the center of this story is called AV coat. It is an ablative compound with a history that goes back to the Apollo program. The Apollo command modules used a version of it, and those missions survived re-entry. That heritage was part of what gave engineers confidence when they applied it to Orion. But the Artemis version of Avcot is not identical to what Apollo used. It is manufactured differently, applied differently, and it was being asked to survive a re-entry profile that Apollo never attempted. And during Artemis I, something happened inside that material that decades of ground testing had never revealed. Here is what the engineers eventually pieced together. Artemis I used what is called a skip re-entry. Instead of diving straight into the atmosphere in a single continuous descent, the capsule dipped into the upper layers, bled off some velocity, then briefly bounced back out before making its final descent. On paper, this is elegant. It spreads the thermal load. It reduces peak heating. It gives mission planners flexibility in where the capsule lands. It looked before flight like the safer option. But physics does not reward what looks safe. It responds to regimes. And during that skip phase, something went wrong inside the Avcot that nobody had modeled correctly. The heat during the skip was not extreme enough to drive full ablation. The outer surface began to char, but not deeply enough, not uniformly enough. The gases forming inside the material as part of its normal thermal decomposition process began building up beneath that partially formed char layer. And the char layer was not yet porous enough to let those gases escape properly. Imagine a sealed crust forming over something that is actively boiling underneath, pressure building with nowhere to go. And then, when that pressure exceeded the structural strength of the partially formed surface above it, the result was not smooth. Erosion. It was rupture. Sections of the heat shield did not gradually wear away. They broke and ejected in chunks before the material could transition into its intended fully ablative state. That was the finding. Not that the heat shield failed under extreme conditions, but that it behaved unpredictably under moderate conditions in a transitional zone that the engineers had not been looking at closely enough. And this is one of the quiet truths of complex systems. Failures rarely happen where everyone is watching hardest. They happen in the spaces between regimes. In the overlap zones where assumptions shift faster than models can track them. So NASA had a decision to make. Do you redesign the heat shield from the ground up, or do you change the path it takes through the atmosphere? NASA chose the second option. They removed the skip re-entry entirely. For Artemis II, the capsule will use a direct re-entry. Steeper angle, single continuous descent. No bounce, no second pass. The idea is straightforward. Dangerous condition was that intermediate heating regime. Eliminate the regime. Push the capsule quickly through the moderate zone and into the high-energy conditions where AVHOT is known to perform correctly. From a physics standpoint, that reasoning is coherent. If you remove the environment that triggered the failure, you remove the failure mode. And engineers also made targeted modifications to the AVSOT material itself, adjusting the geometry of certain blocks to improve how gases move through the char layer during ablation. These are not cosmetic changes. They are grounded in the failure analysis. They are thoughtful and deliberate. But here is what should make you pause. The new re-entry profile has never been flown on the Orion spacecraft, not once. There is no flight data for this exact trajectory with this exact heat shield under lunar return conditions. The first time it will be tested in its full operational reality is when there are 4 people sitting inside. And the models that say this configuration is safe are the same type of models that failed to predict what happened during Artemis I. That is not a comfortable place to be standing. There is a name that keeps coming up in conversations among people who follow this mission closely, and it is a name that deserves your full attention. Not because this person is a fringe voice shouting from the outside, but because of exactly the opposite, because of who he is, what he has seen, and why he is willing to say publicly what many inside the program are only saying quietly. Charles Camarda is a NASA astronaut and engineer. He flew aboard the first space shuttle mission after the Columbia disaster. That mission was not just another flight on the schedule. It was a global test of whether NASA had genuinely learned from one of the most devastating losses in its history. 7 astronauts had been killed, because a piece of foam striking the wing and compromising the thermal protection system during re-entry was understood in hindsight. But the deeper question that mission was meant to answer was whether the agency had truly fixed the decision-making. processes that allowed a known risk to be accepted, normalized, and ultimately ignored until it was too late. Camarda was part of that reckoning. He understands from personal experience what it looks like when an organization gets that calculation wrong. Beyond his flight experience, Camarda is a thermal engineer, someone who understands at a deep technical level how heat shields behave under extreme conditions. And more than that, he has spent years studying not just how aerospace systems fail, but how the institutions behind them arrive at the decisions that precede those failures. That second part is the critical part. Because in complex systems, failure is almost never just a matter of physics. It is a matter of judgment, of how data gets interpreted, of how uncertainty gets weighed, of how risk ultimately gets accepted or dismissed. So when Camarda speaks about Artemis II, he is not speaking casually. He has gone public with concerns about the heat shield decision, and it is important to represent his position accurately because it is easy to misread what he is actually saying. He is not predicting that the mission will end in disaster. He is not claiming that the engineers involved are reckless or incompetent. What he is doing is something more subtle and in some ways more serious. He is looking at the chain of reasoning that took NASA from identifying an anomaly during Artemis II, declaring the system safe for a crewed mission. Why? And he is saying that the pattern of that reasoning looks familiar. Familiar in a way that makes him deeply uncomfortable. Part of his concern is technical. The heat shield showed behavior that was not predicted by any pre-flight model. NASA identified a likely cause and implemented a fix by changing the re-entry trajectory. From a purely engineering standpoint, that is a defensible approach. But Camarda's focus is not just on whether the fix could work. It is on how confidently that conclusion was reached and how much genuine uncertainty remains beneath that confidence. And then there is another layer that does not get enough attention. Reports indicate that Camarda was given only limited access to the full body of technical data surrounding the post-flight analysis and the justification for Artemis II's readiness. That does not necessarily mean anything is being deliberately concealed. But in high-stakes engineering decisions, transparency is not optional. It is structural. When someone with his background and expertise is not fully satisfied by the information he has been given and is willing to say so publicly, that is not noise. That is a signal worth taking seriously. Because what Camarda is really pointing at is not a single technical issue. It is a behavioral pattern. It's a term that gets used to describe it. In engineering culture is motivated reasoning. This is not about conspiracy. It is not about people deliberately falsifying data or consciously ignoring danger. Motivated reasoning is something far more human than that, and therefore far more difficult to guard against. It is the tendency to analyze information in a way that is subtly shaped by the outcome you want to reach, not because you are dishonest, but because you are invested. In the context of a program like Artemis, that investment is enormous. Years of work, billions of pounds and dollars, international partnerships, political commitments, institutional reputations, careers, all of it tied to the success of this mission. And within that environment, even the most disciplined engineers can find themselves asking subtly different questions than they would in a neutral setting. If your goal is to determine whether it is safe to proceed, you ask whether there is evidence that the fix addresses the identified failure mode. If your goal is to determine whether any uncertainty remains, you ask what failure modes could still exist that have not been accounted for. Those are not the same question. And motivated reasoning quietly nudges organizations toward the first one. This is not speculation. Aerospace history has documented it in the most painful terms imaginable. The Space Shuttle Challenger was lost on January 28, 1986, 73 seconds after liftoff. 7 astronauts gone. And the technical cause, an O-ring seal in the solid rocket booster that failed in cold temperatures, was not a surprise to the engineers who understood it. They had seen O-ring erosion on previous flights ahead. Data showing performance degraded in colder conditions. They had raised concerns the night before launch. They had recommended against flying if temperatures dropped below 53 degrees Fahrenheit. On the morning of the launch, the temperature at the launch site was hovering around 28 degrees. Ice had formed on parts of the structure, and the launch proceeded anyway. Not because someone made a single reckless decision in a moment of negligence, but Because over multiple flights where the O-rings had shown erosion and the missions had still succeeded, the anomaly had gradually stopped feeling like a warning. It had become background noise, a known condition, something the system had already survived. And that survival, instead of reinforcing caution, had slowly reinforced confidence. 17 years later, Space Shuttle Columbia broke apart during re-entry over the southern United States. Again, 7 astronauts. Again, a thermal protection system failure. A piece of foam had broken away from the external fuel tank during launch and struck the leading edge of the wing. That, too, was not a new phenomenon. Foam shedding had been observed before. It had been analyzed. It had been classified as acceptable based on the fact that previous missions had survived it. During the Columbia mission itself, engineers suspected the impact might have caused serious damage and requested additional imaging to assess it. Those requests were not fully pursued. The concern was managed downward rather than escalated. The investigation board that examined Columbia drew a direct line between the decision-making that led to Challenger and the decision-making that led to Columbia. Different hardware, different physics, same organizational pattern, to disasters. 17 years apart, one underlying failure of process, that is the pattern Camarda is pointing to, not a prediction, recognition. And when someone who has lived through that history looks at Artemis II and says something feels familiar, that is not a statement to dismiss. That is a statement to sit with very carefully. Here is where everything we have talked about converges into a single point. A single moment. Few minutes of physics that will either confirm everything NASA believes about this mission or reveal something that no model, no simulation, and no amount of institutional confidence could fully prepare anyone for. Let me give you NASA's case first, because it deserves to be heard completely and fairly. NASA's position is not vague reassurance dressed up in technical language. It is a structured engineering argument built on post-flight data, material science, and decades of re-entry physics research. And if you take it seriously, which you absolutely should, it is far more coherent than the public debate usually reflects. NASA believes that the Artemis I heat shield anomaly is not just observed, but understood at a mechanistic level. They are not guessing what happened. They believe they have identified the specific physical sequence that led to the material loss. The skip re-entry created an intermediate heating regime. Avocoat entered a transitional thermal state, where the outer surface was hot enough to begin charring, but not hot enough to establish stable ablation. Subsurface gases formed as part of the material's normal decomposition, but could not escape efficiently through the developing char layer. Pressure built up beneath that surface until the material cracked and ejected in localized chunks. That conclusion is not based on a single observation. It comes from multiple converging lines of evidence. Post-flight inspection of the recovered material. Fracture surface analysis showing how the material separated. Thermal reconstructions from onboard sensor data. Comparisons with high-intensity ground testing. From that diagnosis, the solution follows clear logic. Remove the skip phase. Remove the intermediate heating regime. Remove the conditions that allowed that transitional thermal state to develop. With a direct re-entry, the capsule transitions more quickly into high-energy conditions, where AVOCOT behaves in a well-characterized way. The char layer forms, as expected. Gases vent through established pathways. The material erodes in a controlled, predictable pattern. NASA also points out something that gets underemphasized in public discussion. Even with the anomaly observed during Artemis I, the heat shield still performed its primary function. The crew compartment remained protected. The system did not fail catastrophically. It performed with degradation, not collapse. And they argue that distinction matters because it places the anomaly in the category of performance deviation rather than loss of safety function. The crew has been fully briefed. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were not shielded from any of this information. They understand the nature of the AVH behavior. They understand why the trajectory was changed. They understand what uncertainties remain. And they chose to fly anyway. That choice is not blind optimism. It is a conscious decision made by individuals who understand the risks better than almost anyone else on the planet. There is a kind of courage in that which deserves genuine recognition. And fundamentally, NASA is correct about one essential reality. Spaceflight has never been risk-free. It's not in the Mercury program, not in Apollo, not in the shuttle era. Every astronaut who has ever left Earth has accepted a level of uncertainty that cannot be engineered to zero. The question has never been whether risk exists. It has always been whether the risk is understood well enough to be acceptable. But here's where the argument becomes most interesting and most uncomfortable, because understood well enough is doing an enormous amount of work in that sentence. And the honest answer is that the new configuration, the direct re-entry profile combined with the modified AF coat, has never been flown, not once. There is no flight data for this exact combination under real lunar return conditions. The models say it will work. The simulations support it. The ground testing is consistent with it. But those are the same categories of evidence that existed before Artemis I flew. And Artemis I still produced a result that none of those models predicted. That is the tension at the heart of this mission. It's not incompetence, not negligence, not a cover-up. A genuine and difficult epistemological problem. How much confidence can you place in a model of a system that has already demonstrated behavior outside its predicted envelope? The answer NASA has arrived at is enough confidence to proceed. There are legitimate arguments in favor of that conclusion, but there are also legitimate questions about whether those arguments have been tested rigorously enough against the full range of possible failure modes. Because here's the thing about unknown unknowns, dichotomous. I revealed a failure mechanism that existed in the physics, but was not anticipated in the system-level behavior. It was discovered because it produced visible effects. The material loss was detectable. It left physical evidence that demanded explanation. But that raises a question that sits beneath all the technical analysis. What if there are other failure modes that do not produce such obvious signatures? What if some behaviors only emerge under different thermal conditions, different pressure gradients, different turbulence patterns that Artemis I simply never reached? Artemis I explored one specific re-entry profile. A different profile might expose entirely different interactions between plasma flow, surface behavior, and internal gas dynamics within the AVCOAT structure. And this is the part of the story where the physics becomes deeply personal. Because re-entry from the moon is not just another atmospheric entry. It is one of the most extreme environments any human-made object has ever been asked to survive. Orion capsule hits the upper atmosphere at Mach 32. The air molecules in front of it do not have time to flow around it smoothly. They compress so violently that they stop being air in any familiar sense and become plasma. Glowing, electrically charged, superheated plasma reaching temperatures that exceed the surface of the sun in localized regions. Wrapping around a capsule where 4 people are sitting, waiting. Inside that environment, multiple physical processes are happening simultaneously. Gases breaking apart and recombining, energy transferring through radiation and convection and chemical reactions all at once. The boundary layer, that thin film of gas sitting directly against the surface of the heat shield, either remains smooth and manageable or flips into turbulence. And that transition from smooth to turbulent flow is one of the hardest unsolved problems in applied aerodynamics. It depends on microscopic imperfections in the surface, tiny variations in shape, local temperature gradients changing dynamically during entry. Even the way the material ablates and roughens, the surface feeds back into the flow itself, altering future behavior in real time. It is a system that is constantly rewriting its own rules. And sitting above all of that physical complexity is a human dimension that no engineering model can quantify. Reed Wiseman has a family. Victor Glover has a family. Christina Koch has a family. Jeremy Hansen has a family. These are not symbolic references included for dramatic effect. They're real relationships that exist independently of flight plans and trajectory calculations and post-flight inspection reports. They are the reminder that every system-level analysis ultimately resolves into individual human lives with names and histories, futures that extend far beyond the spacecraft. For days from now, the capsule will meet the atmosphere. It will hit that wall of air at 25,000 miles per hour, and the plasma will form, and the communications will go dark, and for 4 minutes nobody on Earth will know anything. Mission control will be silent. The recovery ships will be waiting. The world will be watching a feed that shows nothing but static. Inside that silence, inside those 4 minutes, A heat shield that has been tested exactly once under real conditions will either hold or it will not. There is no partial success at Mach 32. There is no meaningful concept of almost working when the environment is that extreme. Either the thermal protection system maintains integrity through the full energy transition, or it does not. Either for astronauts descend through the plasma and feel the parachutes deploy and hear the ocean rushing up beneath them, or they do not come home at all. That is the binary reality sitting beneath every celebration you are seeing tonight, every record being broken, every milestone being announced, every image of the moon captured through those windows. All of it, every photograph, every geological observation, every second of that eclipse viewed from beyond the moon, all of it funnels into a single event that lasts only minutes. And that event does not speak in probabilities or confidence intervals or model outputs. It speaks in outcomes. The most likely outcome, based on everything NASA knows and everything the engineering analysis supports, is that Artemis II succeeds, that the heat shield performs, is that for astronauts come home, that the mission becomes a chapter in the history of human exploration written in triumph. That is the rational expectation, and it deserves to be stated clearly. But rational expectation and absolute certainty are not the same thing. And in a system where the final moment is binary, where there is no middle ground between success and catastrophe, that difference carries a weight that no amount of institutional confidence can fully dissolve. The story of Artemis II is not the distance traveled. It is not the records set. It is not the views captured from beyond the moon. The story is the return. And the return will either happen or it will not. 4 days from now, we will know which branch of reality we are, standing in, not through reports, not through press releases, but through whether a heat shield designed, tested, modified, analyzed over years of painstaking work behaves correctly in the only environment that truly matters for it. Everything else is prologue. Re-entry is the truth.